The title of the next presentation is Success and Future of IPv6 from an Electrical Utility Perspective. Our speakers, Sarah Bavarian and Tony Moreau. Sarah Bavarian is a senior engineer with BC Hydro, Protection and Control Design Engineering. Her work is focused on SCADA design, distribution automation, utility telecom networks, and smart grid communications. Prior to this work, Sarah was a DA engineer with the Smart Utility Lab at Powertech Labs and senior engineer with distribution planning team at BC Hydro, working on several automation initiatives including satellite communication to remote assets, downtown Vancouver, open loop pilot, and leveraging smart metering infrastructure in automation of field devices on the electrical distribution network. Sarah worked as postdoctoral research fellow in University of British Columbia, 2009-2012. Sarah has received PhD and Master of Science degrees from Simon Fraser University in 2009 and 2004 respectively. She has over 10 years of experience in telecommunication systems and her research been published in several conferences and journal papers. She's the lead author of book chapter on physical layer of smart grid communication solutions in smart grid communications and networking, Cambridge University Press 2012. Tony Moreau is a specialist engineer with Powertech Labs working with smart grid technologies both on the networking communication side and also with the applications over the network. Prior to this role, Tony was the home area network technical lead at BC Hydro, responsible for the standards technology which supported the development of the home area network program that launched in July 2014. Tony is a registered professional engineer in British Columbia with over 15 years of telecommunications, DSM, and smart grid experience. He has authored numerous articles on home area network and residential energy management, as was being a contributing author to smart energy standards. Thank you.
Thanks for the introduction, and thanks, Tom, for putting an advertisement for our talk today. It's a pleasure for Tony and I to be here today and talk to you guys about the experience we had with IPv6 migration. Can you hear me all right now? Okay. Usually we are talking to utility audience or energy audience, and this is a new experience for us to have. And hopefully, if there are things that you don't get during the talk, feel free to interrupt and let us know. So BC Hydro is the first utility that has set on installing a network that's capable of supporting over 2 million IPv6 devices. And it's a standard-based network, and it's capable of not only supporting the automated meter reading function, but also some of the other applications that we see in near and long-term future, such as distribution automation application and other advanced grid applications. We're going to start with an introduction on, of our companies, BC Hydro and Powertech Labs, and get you a little bit more detail about the smart metering program and what it was and why we went to IPv6 for it. And the deployment strategy of installing such a big network. We would then discuss the unified IPv6 field area network design that we went with, and I'm going to talk to you about the lessons we learned along the way, and that might be interesting for you guys and for other companies that may want to go on the same road. Tony is going to tell you more about some of the testing results that we did and some of the new applications and technology roadmap that we are going for. So anybody here from energy industry or utility industry, does anybody know BC Hydro? BC Hydro is one of the big utilities in North America. It's a crown corporation that provides electricity for about 95% of British Columbia, and it's a huge province. To put it in perspective, you put California, Oregon, and Washington states together, and that's the size of province of BC. So we had a large area to cover, and we wanted a network that would cover all of this province. We have many assets, generation, transmission, and distribution, more than 300 substations, 300,000 transformers, and more than 1.8 million customers that we wanted on this IPv6 network.
So just very quickly, Powertech Labs is a fully owned subsidiary of BC Hydro. So we're slightly different in that we're not regulated in the same way BC Hydro is, so that allows us to pursue commercial opportunities and assist BC Hydro in some future-looking vision applications, which might not really fall under ratepayer applications, so gets BC Hydro ahead of the curve without having to justify some of the expenditures to the ratepayer. We're a very large, multidisciplinary laboratory. So we do things from mechanical testing of poles, transformer blowing up. It's really fun because we get to hear things explode on our campus, all the way down to the group I'm part of, the Smart Utility Lab. We are a relatively new group. We're about 2 years in commercial operation. So just basically helping BC Hydro out today, but expanding out into the commercial market with other utilities. There's about 30 years of specialized engineering expertise. We like to say we have the second highest number of academics, PhDs, in the province outside of academia. So got a lot of long-term asset management PhDs, chemical PhDs, so there's a lot of expertise there. We have 300 customers from around the world. In our hydrogen sector, we actually do work for Toyota and groups like that on their hydrogen tanks.
Thank you, Tony. So for BC Hydro to start this journey, if you remember from early 2005, there was a movement in energy industry talking about how it's time for utilities and energy industry to come into the 21st century and start grid modernization. Obama mentioned smart grid in a couple of his speeches, and that sort of got the buzz going. In terms of BC Hydro, rather than just going and implementing things, the first step was to figure out what we want to do. Where is our vision over the next 30 years? What are the applications we are interested in, and what's the infrastructure we need? Because you don't want to go ahead and implement one application-specific network and then have to do it over and over again as you embark on the other parts of the vision. So this pyramid was actually adopted quite well in the industry across some of the other utilities as well, and coded very well in many IEEE journals. So it shows on the top, it shows some of the applications that are in scope for your utility industry. I don't know if you can read it very well, but smart metering is one of the first that would connect the utilities with their customer base, and it's something that most utilities start with. All of these applications, as you see, are based on three foundations. which is the IT infrastructure, the telecommunication infrastructure, and also some of the advanced electric capabilities. So for us, we wanted to put these IT investments and telecom investments so that it would start from smart metering, but has the vision to go beyond that. But for every project, and you probably all deal with your project managers, you have to have a defined scope. And for us, the smart metering program has some specific scopes that we have to deliver within the life of the project. The first and foremost was installing new smart meters all over the province for each and every customer, which is 1.8 million customers, as I mentioned. And that upgrade has been going on over the last 3-4 years, and now it's complete. We also are working on installing 8,000 to 10,000 system meters. The system meters are meters that are not really monitoring the customers, but they're metering our assets, our feeder ways, our transformers, and the purpose of those is to be able to have visibility over our vast distribution network. And also it would help us to identify electricity losses and also diversions such as theft. Tony was also involved in launching a new in-home display program. So now our customers are able to get real-time feedback on their energy uses and have their apps on their cell phone that they could monitor their usage in real time. And that kind of relationship is a new paradigm in the industry. And last but not the least, this pervasive network and this IT infrastructure would enable us to work on some of the other grid modernization applications, some sooner, some later. But the things that we would like to support are microgrids, distribution generation, and also some of the distribution automation applications, such as volt-var optimization. And these are these grid modernizations. The objective is mostly that we want to be more green and we want to be able to conserve energy and allow for integration of renewable energy. And for those, you need new infrastructure and you need real-time information. There are a few requirements for designing a network of this size and an operational network. And I call this the holy grail of our network design philosophy. It starts with, first and foremost, having measures of security built in and to be compliant with all the regulations. We are a very, very highly regulated industry, so we have to make sure that all of those regulations are met. And the second measure is that we have to make sure our ratepayers are getting a good deal. So we want to have reduced total cost of ownership, not just the capital cost of putting that infrastructure together, but also we want to be able to sustain it over the next 10, 20, 30 years. And that's what makes the utility industry a bit different from your normal IT paradigm, because when we put things in, we want to have it for decades. And that led us to some of the other measures. So we wanted to be, we want equipment and software and hardware that we get from multiple different vendors to be interoperable. And for that, we believe on using a standard-based protocols and equipment. We don't want to be be stuck with one vendor, because that not only limits us in terms of product availability, but also limits us in terms of growth. So any new addition, then we would have to fund it ourselves, and that's not a fun thing. And again, we want a multi-service network that would be able to deliver multiple different applications and objectives. It has to, with the size of our network, it has to be scalable, it's operational, it has to be highly available, and it has to be resilient, because we might not have the resources to go ahead and do field service right away when something happens. And the other thing is, it has to implement quality of service, because not all applications are of equal value and importance for us. And not only just because of NIST recommendations, but because of all these design philosophies, going to IP made sense. We wanted a system that's IP based. This is going into a little bit more detail about those requirements. So having like flexible hardware and software platforms, and we wanted different smart grid devices to be able to be connecting to the same network and have the dynamic connections. We want a network to be able to help our field guys that are working there outside in minus 40 degrees and different weather conditions. And we wanted to grow as new technologies come out. So we would prefer something that's modular, and as new technologies such as new power line communication methods come up, we would be able to add to our infrastructure as we go. I'll let Tony to get more into the security piece later, but again, that's our security and privacy are the cornerstone of the design, and any changes to the system has to go through mandatory security and privacy reviews, especially if it's involved with any customer information. And I'm going to talk more about the standards that are used in our stacks and how we expect it to evolve over the next and over near future. Because of the size of these networks, and because we are looking at such a long-term investment, we ruled out IPv4 because we wanted to have the standardization of IP, but we didn't want to deploy something that's at the end of the life, as Tom mentioned, and we want to be able to expand it as we need it. Right now, we only have 2 million. Maybe you could have done it with IPv4 and tunnels and whatnot, but then the next asset management thing that comes up, but how would that change our IP addressing, and how would that be supported with IPv4 infrastructure? So there has been pains and lessons that we have learned, but I still believe that IPv6 was the right choice to go with this network. And that enabled us to take advantage of all these technologies and advances that has come to the IT industry and bring it to our energy network, such as quality of service and the tagging of the packets and everything. One thing is that this new network would enable us to have enhanced network management, which means now we have a real-time visibility into the whole network, something that in the distribution network was unheard of. Up until a few years ago, only 25% of North American distribution system was even monitored. and that's very, very low. Basically, just the major substations. And even as it is, we are struggling to get smaller substations online because they're in very remote areas. And it might sound trivial, but there are people who rely on that energy, and having that real-time links is very important. So we had tight timelines for the project, and we had the big aspirations. As I mentioned, we had a big list of requirements, and of course, it's always you have to look what's available in the market at the time you're doing your timeline of project. So it was decided to go with a two-phase implementation. We first went ahead and deployed all of the infrastructure, all the networks, all the collectors in the field, all the meters were changed, and with an IPv4 design. But with the capability that we could do future changes all over the air without having to send any field technicians. So the phase one is now complete. We are going ahead to phase two, which is a migration of these 2 million devices over the air to an IPv6 standard-based platform that we will get into a little bit more later, this would enable us to go for those advanced business applications that we discussed earlier. In case you guys may not all be familiar with the mesh topology, our implementation of smart metering infrastructure is based on a mesh topology. So all these meters in the field, they talk to each other and they relay the messages up to a central collector. And these collectors have the capability to support up to 4,000 smart meters. But in practically they are designed to only support 2,000 smart meters to allow us to have failover capacity. If one of them fails in the field, the neighbor could pick up some of the meters from the other. Similar to the mobile industry, each of these clusters is called a cell. But the difference between the cellular industry and this is that in cellular industry, you're talking point to multipoint to all of those endpoints. And here, your connection is not necessarily direct. This gets into more detail of this unified field area network architecture. The area beyond that collector, under the collector, is called a field area network or neighborhood area network. There are multiple technologies that you could use for field area network, and all of them are clumped in a unified architecture. So the application data and traffic could go seamlessly through this layer and go work on whatever technology that's available. One of the things that early on utilities realize is that no one size fits all, so we can't choose one technology and go with it in most cases, and we wanted something that works across multiple platforms. So today, the mesh is our mesh implementation is based on the IEEE 802.15.4G, and it's a RF mesh based. But on the same platform and same architecture allows for power line communication. So if we decide to expand it in the future, it's a relatively easy expansion, and also it could work seamlessly with other technologies that are more known and available, like 3G LTE and Ethernet or fiber where we have it. On top, there are some of the application stacks that we usually use in the utility industry. MDMS, if you don't know, it's meter data management. Load control is very important for utility industry because you want to particularly control your industrial load and big customers. Distribution management system is something that we are implementing in a different project at the moment, and that would give us visibility and advanced applications to be able to control the distribution network. So we have come a long way from that 25% monitoring to today, where we are getting close to doing real-time vault-wire optimization on most of our feeders, and also getting close to be able to restore power to the customers automatically without even sending our field crew. With a physical fix, you would have to send the field crew, but for when you have other sources available, you could open and close switches automatically and limit the area that's impacted by an outage. And if any of you had ever been in a storm situation, got caught by Hurricane Sandy or something, you would realize what an advantage it is to a province or a territory's economy and the well-being of the people. Theft detection I mentioned, and also the advanced metering head-end, which takes care of managing the information we get from all of our customer meters. This would probably be more familiar with you guys. It's your OSI chart for this architecture. On the right-hand side, you see the protocols that you're more familiar with on the file layer, your Wi-Fi, Ethernet, and cellular, and also WiMAX. But on the left side, you see the mesh protocols. So the mesh protocols are mostly used for low power lossy networks. So 6LoWPAN was used for handling the traffic into these low power and lossy networks, because they are quite different from your regular broadband networks. And Tony would explain why was the choice made to go to these low power lossy networks. And Ripple was adopted for the routing layer because for these lossy networks, your links are not always there. They can be getting in and out, fail, come back within seconds. And you have to adapt your routing strategy to be able to accommodate that. And Ripple has done a good job of it. One thing that I can add to that is that although Ripple has all the tools for it, not all the tools have been implemented, and there's still ways to go to get to the optimal routing for these networks.
All right, on these next two slides about security, Sarah and I drew straws because neither of us are security experts, and I got stuck trying to tell you the best I could about our security infrastructure. So as she mentioned early on, we are very paranoid about security in the utility industry, straight from privacy of customer data all the way up to infrastructure protection. So deploying this new setup was challenging because it was one of the first deployments of this type of scale with this type of security in it. So even from looking down at the device level, each one of our meters or any one of our assets that come onto our field network have a certificate in it. That's their device certificate. It says this is a BC Hydro asset, so you can actually go on our network. Then you try to join the network. There's another certificate there that says you can join the network now. So now you're on the network, you got to do something useful. there's an application layer certificate that comes from the application side of things. So now you can exchange information from your head end. So you can collect that metering data by a trusted source. As new head ends come on for things like feeder meters and other applications, they will implement their own application layer certificates. So it allows us to be very, very detailed, very, very secure. And because we're in a group here of IPv6, if I didn't say IoT, I'd probably not be allowed to come back. So this is probably a model that you will see starting to propagate across other industrial Internet of Things deployments, just because security is so important. And without going into much detail, you guys can take a look at the various points here just to take a look at what we did in our infrastructure. We used as much as we could that was standards compliant, so nothing was reinvented. Standard certificates, 802.1x, and everything that's known in the IP world.
What I can tell you is that, what I can tell you from experience is that when we were trying to do some lab testing, the coupling from those layers of security, trying to do some basic file layer testing was a big pain. Because it's so decoupled, it's so ingrained in it that taking it out was almost impossible. So where we are today is that we are in the middle of migration to IPv6, and it's a gradual transition. We don't want to break a working system. It's just such a new paradigm for us, and I think for anybody, to have a network with 1.8 million working endpoints to upgrade over the air and make sure nothing breaks, because you don't want to piss off the operation folks. So it's a gradual transition scheduled to be finished sometime in 2015. Last month when I was talking to our project team and making these slides, 3 of the cells were already completed successfully. Our wide area network infrastructure is all in place and being operationalized, and we are starting the transition to multi-service grid network. Basically, our feeder meters and transformer meters are in field trials. We are developing the analytics suites for theft detection. And in the lab, Tony's team is moving ahead with testing distribution automation use cases on this IPv6 RF mesh network. There were many lessons learned along this journey for us, and they were in multiple different areas. So on the planning side, we would recommend whoever is going to embark on such a journey is to use, to make sure all the licensing and agreements are there in place with the vendors. You have to know what skill sets you need and make sure you plan for it in advance, and who's going to provide them, and are you going to recruit them yourself, are you going to contract it out? And also plan your deployment process in a way that field technical requirements is minimized, because you don't want to be in minus 40 degree outside programming a router. You have to make sure things are done in a way that they can be all done in the back end. You have to have rigorous process for testing for any change as they come up, and have non-production environments to allow those testings. For early applications, even the non-product is not a good idea. Just going for a lab testing, lab environment is the better idea for early applications. On the planning side, it was a pleasure to see what we have coming up in the talks in this conference, because those are touching on whatever lessons learned we had in our process. First of all, you need IPv6 training. You really do, and you need to provide it across the board to your PMs, to whoever is involved in that project. They may have a loose idea from university days what IPv6 is like, but they need to have the understanding of all these changes, and such as subnet masking. You have to do device audits. There are lots of legacy devices that say they're IPv6 compatible, but they may not support all the options, such as multicast, and there would be gotchas and expenses on the way that you didn't expect. The other aspect, and Tony would touch more on that later on, is the MTU size. So each layer of application and security would add different headers on your packet, and that would get your MTU size bigger and bigger and bigger, and might lead into fragmentation along the way. And the fragmentation is not a good thing in this case, because some of the times your routers may drop it. It might cause delays that are not satisfying the application requirements. So planning and understanding your network MTU size is important. There's also two different networks that you're dealing with. The field area network, or NAND, which is your low bandwidth mesh or power line communication system, is very, very different from your back-end IT infrastructure and wide area network. So understanding those differences and having your IT team deal with it is a must. You need to look into your IP address planning, and having band-aids such as NATing your existing IPv4 network to IPv6 network is not a good choice to go, because as Tom mentioned, it would be expensive and hard to sustain, and it would also expose you to a lot of security issues in future. So we went ahead, and we had our IT team went ahead, and they had an overall IP plan that included all of our existing and what we expect in the future, both on the corporate side and operations side. We still have dual stack in the back end. Who knows what's happening in the future? But for now, that's what we are implementing. On top of IP address plan, you also need a new routing plan developed for the system. And what we ended up with was OSPF in the data center and BGP for the smart metering program. So we had to do a BGP over OSPF routing plan for the system. And the resilience and high availability was a requirement, not in the edge, but in the back end. So in the back end, you don't want one router failing and your whole smart metering system going down. So you need to build resilience. And again, not only for one head-end system, but also you would have to build resilience in terms of the geographic exposure. So, for example, we have two control centers, one in Vancouver area, one quite far away in Vernon. So, if there is an earthquake, there would be all the control and operations would be transferred seamlessly. On the implementation and operations side, this is a completely new paradigm for us. It's a network that is highly complex, and getting into this new system where IT and operation of the energy network are getting closer together is a new challenge for us, and we're excited about it. There are lots of things happening in the course of the project, and you have to be creative and flexible to be able to catch up. And you need to have procedures in place so you could handle the different priorities and different project streams. Network management. So on network management, you have different technologies in this network, on your WAN, on your devices, and you would end up with multiple network management systems, however you look at it. And having the skill sets and having the operations and maintenance of all these network management systems is a challenge. And I don't see any easy answers and workarounds about it. You try to have them migrated into at least the monitoring part into one, but when it comes to maintenance, you usually have to go for device-specific network management tools. And this system brings about the issue that before a utility would go implement something and you leave it for 30 years and you don't have to touch it unless something breaks. But now you have a living, breathing system. So you have to have constant upgrades, constant things that are happening. And this is very new for us and for the industry to understand and build new processes around it. And this is something that we are in the middle of right now.
So we'll change gears just a little bit and go right down into some details here. But before I start diving down into the mesh testing, I know some of you are probably thinking, well, you got a cellular network out there. Why didn't you just put cellular under glass in the meters and forego this low bandwidth network? Well, there's a few reasons that we thought through this one. First off, cellular networks evolve very quickly. So if you have 1.8 million meters out there and now your carrier decides they want to go to the next latest greatest, you've got assets that are stranded. And now you might have a 5-7 year plan on these things and we have to put them in the ground for 25 years. So that's one reason. The second one is bandwidth. One of the carriers one of the utilities back east chose to do cellular under the glass. They've been given a window of 2 hours per day where they can do meter reads. Not exactly an interactive network if you think about it. We've deployed an IoT platform here. This is one of the biggest IoT platforms in the world now. So you've got to start thinking about sensor data. If we don't want sensor data, why are we doing IoT? So this is another reason. And I'm sure you've read the articles out there that are starting to say the networks of today are not scalable for the networks of tomorrow. And what do you mean by that is you've got sensors that don't require YouTube videos flying to them. You've got data that's coming back, and it's small packets of data. So you don't need megabits upon megabits of data to these sensors to get the value out of them. So you might as well start looking at a lower cost, lower data, about 30 kilobits per second is what we're getting on these things, as opposed to spending huge dollars on bandwidth. So now you have that sort of framework. It might give you a little more interest on why it's important to understand these low bandwidth networks going forward with IoT pushing so hard. So one of the things that we have to remember on these networks that packet size becomes an extremely important factor. Too large of a packet size will impact the performance on the network. And that drops to the next stage. Sarah mentioned 6LoWPAN, the adaptation layer between the Ethernet framing down into the 802.15.4 network. Well, fragmentation gets introduced. Too large of a packet size, now you might have 5 packets flying out on your mesh. That's going to increase your latency and potentially see some drops out there because this is not a reliable network by any means. The performance of the mesh not only depends on your packet size, but also the hop depth. So everyone's familiar with adding routers increases your latency, but this is even more apparent in a mesh network where hops will actually add headers, they'll make the latency increase, and the farther you get down, and we've seen this in production, if your packet sizes get too big, the endpoint can't process it in time, and time's out. So now you end up with meters that might lose configurations, not take a setting. So it's very important to start taking a look at your hop depth. One of the things we're hopefully going to see out of IPv6 and implementation of Ripple and some of the new things, it's going to flatten our current mesh, which can be, in some cases, 30 hops down, which is a pretty substantial depth in a mesh. The other piece, and I just called out distribution automation because that's the first application that's going to go on top of this beyond metering, is you really need to understand the traffic. Application developers need to think about what they're putting out there on the air now, whereas in today's broadband world, you just create something, who cares how big it is? You fire it out there, there's bandwidth. Here you got to start getting those guys down and talking to the networking people to understand what's going out on the mesh. So in case you aren't familiar with 6LoWPAN, I thought I'd throw up a little slide here. It sort of gives you the idea that, yeah, this is a constrained packet here. So you toss in a great big packet, and you've got to break it down. So you can see the different byte sizes here. And this is what I'm talking about, the fragmentation. Your standard IPv6 datagram will get chunked down into a number of packets, and if you lose one of those on your mesh, well, you got to do the whole thing again. So it can cause quite a bit of problems with inside your applications, especially if you haven't designed them for that type of environment. Ripple. Well, I'm not a Ripple expert by any means, but it is a new protocol. It really only has about 2 years of experience out in the field. It was implemented, you probably know, in Zigbee, Smart Energy 2. It was implemented there. It's now part of the Cisco infrastructure and moving towards things like YSUN. So it's a technology that's going to evolve over the next few years. It's unique in the fact that it is one of the first routing protocols for a mesh network that lives above the IP layer, because a lot of other technologies, they mesh under as opposed to route over. So it's unique. You've got to take some interesting looks at this, because you can't always guarantee that the hop points are going to be powered. They might not have enough power to transfer, so Ripple has to take that into account. So they have to be able to build your paths back up to your DAG using paths that are reliable. Some sensors might look like a good path, but they might not be a good path. So the protocol has to take all this in. And at this level of development, some of that stuff's not there yet, so we're living through some of the growing pains of the infrastructure. Now, one of the things we heard in Tom's talk was that you got to get away from this IPv4 thing. This thing sucks trying to NAT this into V6, but it's not going to be the case for utilities. We've got hundreds of assets out on poles that even at IPv4, these things are rudimentary. You have to remember that a lot of these device vendors are utility-centric device vendors who someone told them, you need to put an Ethernet port on your device, so they did. They didn't understand what they were putting on that device, so it barely works with IPv4. And we're not going to get those field devices to IPv6 anytime soon, and we're not going to see our distribution automation guys wanting to go out there and switch these things, which have been in the field for 5-10 years and are working just fine, not connected, but now we want the data off them. So what we've done here is our first generation will likely use MAP-T, which is a NAT64 based protocol to do a V4 translation or tunnel to our back-end servers. And that's why some of our servers are going to have to run dual stack for a long time. So I just wanted to show you sort of the way we've been testing our networks. One of the key aspects on, especially with distribution automation, because it is legacy applications, is to really understand how that traffic works. This stuff has been tested on cellular links, it's been tested with Ethernet, broadband stuff. So you can do a lot more cool applications with that than you can on a mesh. So what we had to do is we had to benchmark it. So we cabled up these networks, we put our distribution automation things out there, and we looked at the traffic and understood how that traffic actually flew across the mesh or across the Ethernet cable. Once we understood that, then we connected it up to a product that Cisco will be having out in a little while called the IR500. It's a little distribution automation gateway, so you can plug V4 devices into it and it tunnels them for you. So we plugged that in there, and then we started running this stuff over top of the mesh. And we started taking a look at the characteristics, where it was dropped, what was going on. Out of that, we were able to start looking at things, packet size and round trip time. So we tuned applications, we did some performance testing on there to understand how does packet size affect the performance on this mesh. And as you can see, it looks not too bad until you hit that 6LoWPAN fragmentation point. And then everything just starts going crazy. And you take a look at some of the packet latency times here, and applications, when you're talking distribution automation, which might have a more real-time sense to some of the use cases, just doesn't work. Just as a demonstration, when I was mentioning hop count, this is actual testing that we've done to see what effect does hop count have on this thing. And at this point, we've only tested 1 and 2 depth on the mesh. And we're looking at trying to do 3, 4, 5 so we can start developing a pattern. Is it linear? Is it nonlinear? Just so we can understand how this is going to affect throughput and packet loss. The next one that has been a very strong debate inside mesh networking is TCP versus UDP. So a lot of the legacy applications today use TCP. It was an easier protocol to develop for. got that great connection-based stuff there. But mesh networks, it may not be the right technology. So what we did is we quantified the two different protocols to understand benefits, cons to using them on the mesh. And you can see the performance information there. The one thing that we did find out of it is a lot of these legacy devices don't have an opportunity to go to UDP. So we're going to have to live with TCP, and we're going to have to understand how that's going to affect our use cases. And over time, we can inform application developers, or hopefully they learn from this first touch into the Internet of Things, how to develop their applications that might work on broadband or mesh networks. Now, this is the stuff that gets all of us back at Powertech very excited. It's the future of the mesh for utilities, and it actually is the future of the mesh for IoT applications. So you've probably been, I don't know, living under a rock somewhere if you haven't heard about Cisco's fog computing. Well, this is one implementation that is really going to drive some changes to the industry. So you can see on the left-hand side, the traditional computing model, everything goes back to the data center, to the cloud. It's dealt with there and then back out to the endpoint. Well, that works great for broadband, not so great for low bandwidth sensor networks. You don't want to take all of that data. Sensors chirp, they chat, there's a lot of stuff in there. You don't necessarily need to know everything is okay for every second. You want to know that everything's okay every couple hours, or, oh my God, something blew up and we've got a fire going on here. So what we've done is we've started looking at the IoT computing model, which takes the intelligence that's in the data center and pushes a bit of that out to the edge. So what that allows us to do is we can actually monitor that okay out at the edge without having to ship it back and make decisions on whether we need to alert on things. So one of the really cool things is this has all been sort of fiction. There's been a lot of marketing brochures. Cisco has products out, but there haven't been any applications taking part on this. So if any of you have colleagues that are out at UTC Canada right now, we've actually got a demo set up out there between Cisco, a company out of Vancouver called BitStew Systems, and Powertech, where we've actually taken a BitStew application, which they took their central data center solution, they pushed it down to a Cisco grid router, small footprint. They're able to monitor SCADA traffic, distribution automation traffic, and based on the signatures of how the traffic is flowing, they can tell this is normal use case, or they can tell this is an alarming use case, and then alert a central system. Because a lot of SCADA systems aren't real-time information to the operator. The operator has to go back and do investigation. Is the telecom link broken, or is this actually a distribution automation problem? So we're actually building that intelligence out at the edge. So this is very early stages. Next stage would be to look at things like distributed SCADA master systems. So you actually have control out at the edge doing intelligent things. So if your data model for your network, you can say there's a couple of reclosers out there. I'm on one CGR, one went down. I can dynamically change the metrics on the other ones to accomplish various field performance. I'm not a SCADA guy, so I can't get into that level of detail. And this just talks a little bit more about the architecture of the platforms that we're starting to use out there. So the traditional router is an iOS for a Cisco router that's just sitting out there. Well, what we've seen develop now is they basically implemented a hypervisor. They've run iOS in a virtual machine, and then they run a Linux guest OS on there. So the opportunities for application at the edge now becomes as limited by your software developers and their ability to work in a small footprint. So it really is a game changer when you start thinking about the intelligence you can push out into the IoT now. You no longer have to rely on your data centers to process everything. And that really was just trying to give you a flavor of what we're doing in the distribution automation, in the future-looking aspects, and where you can possibly start thinking about this mesh technology going forward into the IoT. We're hoping that people are now starting to recognize the learnings from the utilities really should be looked at as learnings rather than going through the pain and suffering that we've gone through ourselves trying to get to this. So at this point, we'll open it up to any questions. We'll start over on that side there. We've got a microphone here, so they'll just bring it out.
So I've been looking at the cyberspace modernization part of the grid and looking at the IEEE 2030 specification that is completely absent of this kind of language and standardization. How do you you see that developing for standardization? So IEEE 2030 spec to all this cyberspace modernization.
Thank you for bringing that up. I was actually part of the committee that reviewed IEEE 2030 at the time. IEEE 2030 is the conceptual model of this arena. So it was based on the based on the NIST guideline and the understanding what were the actors and what are the pieces of the puzzle that is in the utility network. So basically, gave us a model where you build on the understanding. It was the first step to understand the utility architecture, and then. As we moved in more towards the implementation, we had to adopt more of the detailed approach where you have the IT models now understood. But there is going to be a lot of work actually about gelling all those things together. And it's not just for IEEE 2030. You have a lot of standardization bodies on the energy side, and utility side, and automation side that have different languages. And merging those IT/OT languages is going to be what we're going to have fun with over the next decades or so. So, for example, utility industry has a lot of language around asset naming, asset qualities, asset objects, and also about the data naming. So each piece of data, we have a standard called IEC 61850. Anybody familiar with that? So that's where, as a protection expert, I would have to be more involved with, and that's the telecom based protection language that we use. So each piece of data is an object that has names, and it just comes from a protection background, but it also has some of the IT concepts in it. So merging those naming standards with what you have in the IT world and computing systems is something that's just being worked out now.
Any comments on the experience with addressing mechanics and like SLAC versus DHCP, privacy extensions? How did that work at large scale and across sensor networks and things?
Well, our infrastructure has been kind of limited to the architecture that's been provided by Cisco in a lot of cases. So our IPv6 addressing is on our endpoints is provided via DHCP. We didn't really have any option to take a look at that. So one of the things we have done in there is for our infrastructure, using option 17 extensions in your DHCP is very important to us because it allows us to tell different endpoints who their head-end servers are. So that's one of the challenges when you have a very differing sensor network out there. Anyone else?
I was just curious, how meshy, for lack of a better term, are your cells? Does every single device in the cell have redundant connections, or is there a significant fraction that has only single connectivity, but overall there's enough mesh to make it work?
Yeah, so it really does come down to geography. In our metropolitan areas, things do mesh. You've got a lot of sensors out in a very well meshing environment. But when we get out to the really rural areas where you might have farmhouses every kilometer from each other, it starts looking like a very long, they call it a string of pearls. So it depends on your network deployment.
Any numbers that you could put around that? Percentages?
No, I couldn't tell you with any sort of certainty. And right now, most of our meshes are the V4 solution. So we're going to see that change pretty dynamically as soon as we start rebooting our routers onto V6.
Thank you.
Well, thank you very much.